Now the next model is the model where we subtract slope to create periodicity. And basically this is used in bounded additives. So when the function is Cauchy additive but bounded, so here we linearize it by taking gx as fx minus fp upon p into x. And what we'll do here is simply take up an example. So here we are given a function f from r to r and it satisfies Cauchy's equation. So we are given fx plus y equals fx plus fy, and it says there exists some interval c to d which is real numbers such that c is less than d, where f is bounded below on all c, where f is bounded below. That means this fx is always greater than or equal to some number m in this interval c to d. Now this first part is show that fnx, it is nfx. Now this is pretty standard in Cauchy's equation and we have proved it again and again. So this result we want to skip. So fnx is equal to nfx for n belongs to z and x belongs to r. We have proved it previously. Now this part B is define P as D minus C and show that f is bounded below on the interval 0 to P. Now when x belongs to 0 to P, x plus C will belong to C to P plus C, which is D. Now in this interval we can write any fx as f x plus C minus C. Now using Cauchy's additive identity we can write fx plus C plus f minus C, and we also know that f0 is 0, and if we put y as minus x we'll get f minus x equals minus fx. So a Cauchy equation is an odd function and f0 is 0. So f minus c is minus fc. So it is fx plus c minus fc. Now this x plus c, it is bounded below. So this fx will be greater than a minus fc. So this fx, it is bounded below in the interval 0 to p. Now its c part is define a function gx which is fx minus fp upon p into x in the interval 0 to p. Now we have to prove this gx is bounded. Now in this interval 0 to p, this fx, it is bounded. Now this x, it lies between 0 and p. So this constant fp upon p into x, it's also bounded. So this gx, it is bounded in 0 to p. So in this interval 0 to p, this function gx, it is bounded. Cauchy's additive equation. Now in the next part it says, prove that G is periodic with period P. Now Gx plus P will be Gx plus Gp, and Gp will be Fp minus Fp. So Gp is 0. So this Gx plus P, it is Gx, or Gx is periodic with period P. And because it's a periodic function, G is bounded in x belongs to R. We have proved our fourth part that G is periodic and is bounded in R. Now is suppose there exists some x naught for which g x naught is unequal to 0. Prove a contradiction by showing that the sequence of values g and x naught is not bounded below. So for this e part, we let g x naught is unequal to 0. Now we have already figured out g and x naught, it is n times gx naught. So we'll get values plus minus gx naught plus minus 2gx naught, and these values, they'll keep increasing, which means this g is unbounded, which is a contradiction. That means for any point gx naught, it must be equal to 0. That is, gx is a constant function and it should be identically 0. And if gx is 0, we can write fx minus fp upon px equals to 0, or your fx is some ax, where a is fp upon p. So this bounded below condition also gives us regularity in Cauchy's additive equation.